guys, welcome back. I'm Jingyuan Liu from Xiamen University. So today let's start to discuss Chapter 2, Characterizing and Displaying Multivariate Data. From Chapter 1, you already know that how to understand multivariate data, right? How to represent that. But how to extract useful information from multivariate data, this is the task of Chapter 2. So this is kind of the foundation for later chapters here. Okay, so here is the outline for Chapter 2. We will start with a review of univariate case, where we define the mean, variance, and standard deviation. And also for two-dimensional case, we define the covariance and the correlation. And also how to display them using graphs for the univariate and bivariate case. So this part will be fast because you already learned that from other statistics course. And in the second section, we start to talk about the characteristics for random vectors instead of random variables because we have p-dimensional now. How to determine the matrix presentation of multivariate data, and how to define the mean vectors and covariance matrix or correlation matrix. Okay, and how to use sample covariance matrix. And also how to use graphs to display the multivariate data here. And also in section 3 and 4, we will cover some additional topics, including the partitions of random vectors and also the linear combinations of random variables. Okay, so now let's first review the characteristics of random variables, including the mean, variance, and standard deviation. Let's start from the random variables. Here I use capital letter Y to denote the random variable. And for any random variable, as we already learned in mathematical statistics, we can define its mean or say expectation. We call it mu here with this definition. And also we can define its variance, sigma square, or sometimes you call variance of Y, which is defined using this expectation. So here as a typo is Y minus mu, okay? Square. And also the population standard deviation, which is the square root of the population variance. And for random sample where you actually have data, then you can estimate the population mean, population variance, and standard deviation using the data information. Here we call Y1 to Yn, n is the sample size. So we should have the so-called sample mean, sample variance, and standard deviation. So one thing to notice is here you have n-1 instead of n in the denominator of sample variance. The reason is you just use 1 degree freedom to estimate the population mean using Y bar, the sample mean here. Okay, so remember that this one is the so-called unbiased estimator of the population variance, instead of when we use MLE where you have n instead of n-1 here. Okay, so for the bivariate case where we have two random variables, then we can define covariance and correlation. Okay, so when we call bivariate, bi means two, right? So that means we have two random variables, x and y. We can define the population covariance by the expectation of this product here. Okay, so from mathematical statistics, we know that it measures the co-movements between x and y, right? X goes larger, y goes larger, or x goes larger, y goes smaller. Okay, and for population correlation, we need to remember why do we need to bother to define such a correlation. So it's the idea of standardization, right? Because the magnitude of covariance doesn't mean anything. Okay, only the sign means whether it's negative or positively correlated. But the correlation here means something, the magnitude, right? Because it's from -1 to 1, okay? Okay, so again, when we have the data set or the so-called sample, but here notice we have paired sample, okay? So the data set looks like this, still with size n. We still can define the sample covariance and sample correlation as estimators of population covariance and population correlations, okay? And again, notice here, we still have a -1 to guarantee the unbiasedness of the estimators. And because we still use 1 degree freedom to estimate the mean. But you might ask, here we have two means to estimate, right? but why we still minus 1 instead of minus 2? Okay, that's because actually, so you can see it from the data set. So this x1, y1 actually belongs to one data point, right? So mu x, mu y is indeed one pair of random variables to estimate, okay? Instead of two separate random variables, they are a pair, okay? You can consider them as a vector. So still, the degree freedom is used by 1 instead of 2. And also we have sample correlation by this definition, okay? So sample covariance divided by, we use those as sample standard deviation. Okay, now let's talk about some remarks related to covariance and correlation. First of all, you should notice that the definition for covariance or correlation equals to 0 means what? Means they are only linearly independent. Okay, we cannot guarantee they are completely independent. They might be quadratically dependent or non-linearly dependent, so on and so forth, but they are linear. Okay, so you should remember why here, right? You can connect this with linear regression. But although we know that covariance or correlation equals to 0 doesn't mean they are independent, but in a special case, they are equivalent. Okay, so which special case? Hope you still remember. So if x and y have a bivariate normal, so under this assumption, then covariance or correlation equals to 0 if and only if they are like x and y are independent. Not only linearly independent, but completely independent. Okay, so in chapter 3, we will start to talk about multivariate normal distributions. By then, you should know that why do we have such a case? Okay, so that's because when x and y are bivariate normal, their relationships can only be linear. Okay, so we will talk about this later. The third one is the sample covariance is proportional to the slope of the simple linear regression line of y against x. So why is that? We know that the sample covariance, sample correlation actually measures the linear relations, right? So it should be analogous or proportional to the slope because the slope also measures the linear relationship between y and x, right? So if you remember, I can show you the format of the estimated coefficients in linear model. Here, beta 1 here. So beta 1 hat, in the simple linear regression model, which is the coefficient of x, should be just the sample covariance over the sample variance of x, if you remember. So this is proportional to this as xy, right? So the only difference is this. Of course, this sxx is just sx squared, right? Okay. The next one is about Rxy, the correlation between x and y, sample correlation. It is the cosine of the angle. Actually, from the definition, you can easily verify this, right? The cosine of the angle, because we already reviewed this in chapter 1 when we review matrix algebra. So according to the definition, it is just the angle between this vector and that vector. So it's just the sample vector after centralization, after minus its mean. Okay, so notice that this is happening in the sample space where it's n-dimensional sample space here. Okay, the dimension is n. So it's not in the vector space, it's not in the variable space. So it's in the sample space. So if Rxy equals to 0, that means you have a 0 sample covariance. We call the corresponding two variables to be orthogonal. Okay, so the orthogonality just means the two variables are linearly independent. Okay, and the last piece is talking about the graphical display, how to intuitively and visualize the univariate data, univariate variables and bivariate variables here. Okay, so as an example, let's consider the data set of the height in inches and weight in pounds for a sample of 20 college-age males. So in this table here. So you can see that for each person, we have two-dimensional measurements here, height and weight here. Okay, so how to visualize such a data point, such a data set? You can just think about it in your mind first. Okay, when we only consider the one-dimensional measurements, like for example, we only consider height or we only consider weight, we can use the so-called dot plots. Okay, so this is also a kind of scatter plot here. Okay, so we just represent those in such a plot when we have two measurements, and for each person we have its corresponding measurements of height and measurements of weight. Of course, you should have different measurements here. So this scatter plot, univariate scatter plot, is not so frequently used because we only have univariate. Okay, we know that scatter plot mainly display the relationships between two variables. But we can still extract some useful information. Like we can know the sample mean, the sample standard deviation of height, and sample mean and sample standard deviation of weight. Okay, and from the univariate scatter plot, although you plot them separately, you can still find some trend or see pattern, right? So like for example here, when y goes large, x also goes large as well, right? So they tends to covary, and the trend, you can see the trend is more or less covary as well. A more efficient way to display the relation between the two variables, height and weight, is of course the so-called bivariate scatter plot, which is our frequently talked about scatter plot in reality here. Okay, so here we have two axes. X-axis stands for height and y-axis stands for weight. So we can see a clear trend, like the positively correlated trend here is very consistent with the linear regression line. Okay, so to represent the relations between the two variables. Also, you can evaluate the relations, positive relation, using the sample covariance and the sample correlation. So from the magnitude of the correlation, you can detect a very strong linear relation. Okay, now we have already finished the review of the characteristics of the univariate random variables in the first sections. So from next section, we will actually start to talk about the random vectors instead of variables here. That means we have more than one dimensions to consider. Okay, so see you in next section.